All right, guys, so we're going to talk about exponential functions. So what you can see here is we have an exponential function f with a base a. So f of x is equal to a raised to the x. And you see that a has to be greater than 0, a cannot be equal to 1, and x is any real number. So let's go ahead and take a look at some example here. So we have f of x equals 2dx. Let's take a graph and talk about what we see. So if I were to graph this right here, I'm going to go ahead and make my table, XY table right here. And let's go ahead and start off with -2, then we'll do -1, 0, 1, and 2. So if I were to put in these values here, this would be 2 to the -2, which gives me 1/4. This would be 2 to the -1, which gives me 1/2. And then 2 to the 0, anything to the 0 power is 1. Put in 2. So this would be 2 squared. Oh, sorry about that. Go back to the first power, sorry. Gives me 2. And then put in 2 now, which would give me the 4. So if I were to graph this, I have -2 and 1/4, which would be somewhere over here. -1.5, 0, 1, 1, 2, and then 2, 4. So this graph will look just like this, pretty close. And you can see from there, it is the exponential growth. You might remember that from science. So this is our growth function right here. We got 2dx. Now we're going to notice some things about this. No matter what value I put in for x right here, I'm never going to get that equal to 0. I'm never going to get that equal to 0. So first, talking about domain, you can see that this is going to go forever to the left, and it's going to go forever to the right. So my domain is all real. Now this is true for all the exponentials, assuming we don't have any transformations, which I'll do in the next video. Then we talked about the fact that you can't get this to equal 0. So that means I have a horizontal asymptote at y equals 0, which makes my range, if you think about this, if this is never going to touch 0, but it goes up forever, that means my range is y is greater than 0. And then last but not least, we have a y-intercept at 0, 1, which is right here. So all of these characteristics right here will apply to your exponential function, assuming that you do not have any transformations, no transformations at all. So let's look at, if I just change this up a little bit and say f of x is equal to 2 to the -x, 2 to the -x. And what you're going to see is that will cause a reflection in the y-axis, and thereby giving us the decay model, So if I go ahead and put in the same values, what I'm going to get here is, oh, I'm sorry, fix that value there. So I'm going to get 4, 2, 1, 1/2, and 1/4. So at -2, I'm now at 4. At -1, I'm at 2. Notice that the y-intercept is still the same. Then I have 1.5 and 2.25. So hopefully you can see that this is definitely a reflection through that's not showing up. It's a reflection in the y-axis. It is a reflection in the y-axis. All of these points here, they would all overlap if you were to fold it over the y-axis. All right, so let me talk about one other function. So we're talking about exponentials, an important one here, and that is called the natural base e. So what we have, I'll just call this number 2. You have f of x is equal to e to the x. So e to the x, let me just fix this. I'm trying to, it didn't come out right, and now I'm trying to rush. There we go. So if you take the expression 1 plus 1 over x raised to the x and evaluate it as x goes to infinity, what you get is a value that approaches 2.71828 ... It keeps going on forever. Think about pi, 3.14, keeps going on forever. And that is similar to the natural base e. E is the natural exponential. They call it the natural exponential because it arises naturally in math and in the physical sciences. Again, just like pi does, arises naturally in geometry. And of course, you're going to see this when we talk about logs, and then we'll bring up the natural log. That's why I'm bringing it up now. But if you were to graph it, you would see that it's going to look just like any other exponential because e is a number. It's just an irrational number. So if I were to do the -2, -1, 0, 1, and 2, and this 2 did not come out great. So if you were to put those values in there, you would get approximately, it's 1 over, this would be 1 over e squared, which is about 0.1353. This would be 1 over e, which is 0.3678. And then, of course, this would just be 1. Notice we have that same y-intercept. Even though we have a different base, we still have that same y-intercept. This would just be e, which we already said was 2.718, and then so on. And then this would be e squared, which is about 7.389. So if you were to do a quick sketch, you would see that you're going to get the same. So at -2, you're somewhere down here, -1, 0, 1, and then here, and then somewhere up here. Again, this is a rough sketch, but just so you can see, you get the point of what this would look like, which it looks just like this one right here, which is 2 to the x. So again, your exponential functions, you have your growth, and then you have your decay, which of course would be a reflection in the y-axis. We just talked about the natural base e, and you can have any base. It doesn't have to be 2. It could be 3, 4, 5, but it's important to talk about the natural base e because, again, that's going to come up. So in the next video, what I'm going to do is talk about transformations of the exponential functions, and then after that, we'll probably move on to interest and then go to logs. So I will see you in the next video.